All right, everyone, in this video, we are going to discuss when we need to protect an aldehyde or ketone. Now, acetal functional groups can be used to protect aldehydes and ketones. That is to say, when we generate an acetal, we essentially make the aldehyde or ketone inert towards being reacted. So if I were to take this aldehyde and turn it into an acetal, that carbon of the acetal is no longer an electrophilic carbon. The carbonyl carbon is absolutely an electrophilic carbon and could be attacked by all sorts of nucleophiles, but the acetal is a pretty inert species, and therefore it can be a protecting group for aldehydes and ketones. That being said, the acetal itself will be stable under basic and neutral conditions. That means it would not react with the Grignard reagent, it would not react with a hydride donor, it would not react with an amine. So it's a pretty good protecting group for aldehydes and ketones. But acetals, they can be reversed back to the carbonyl form. We could remove the protecting group, regenerating the aldehyde/ketone from which it was derived, using aqueous acid, water, and acid. And one conceptual note is that no heat is required to deprotect, although certainly heat could be used. So in this video, we're going to go over the various instances of when we would need a protecting group. Then we're going to go through some examples, just walking through examples where protecting groups have been utilized. All right, so in a former video, we showed this visual here. If you have an aldehyde or ketone in a structure, and then there's an alkyl bromide and you're wanting to turn that into a Grignard, we cannot just directly put in magnesium and diethyl ether, because the Grignard that you would form would react with the aldehydes. Yikes, right? And then that's a huge mess in solution. There's going to be no viable Grignards left. The Grignards would attack each other, kind of having a civil war in solution. And so if our objective is to actually make a new carbon connection, which would need to be generated using a Grignard reagent, what we can do is actually protect that aldehyde or ketone prior to forming the Grignard. So that's example and instance number 1, protection prior to forming a Grignard reagent. When we react with our 1,2-diol and catalytic acid, we will form our cyclic acetal protecting group. Then it would be safe to prepare a Grignard. Step 1, we prepare the Grignard reagent. Let's visualize having MgBr now. We could then attack formaldehyde, break the pi bond, then do a workup step, and that would create this new carbon connectivity shown on the right side of the structure. We attack the carbonyl carbon, broke the pi bond, and protonate to make an alcohol. Then after we're done using that Grignard reagent, we can deprotect. We can react with aqueous acid, and we essentially remove that acetal protecting group, severing its connection. We regenerate the 1,2-diol, which would be a byproduct. And that result, we regenerate the aldehyde/ketone that we originally protected. So instance number 1 is using a protecting group prior to forming a Grignard reagent when we have an alkyl bromide and an aldehyde or ketone in the same structure. Gotta protect prior to Grignard reagent formation. All right. Scenario number 2. Let's say that the objective in a synthesis is to preserve the aldehyde net result, but react selectively at the ketone. That would be an instance where we'd also need to use a protecting group. Notice how here we formed a new carbon-carbon bond, and that would indicate that a Grignard reagent was utilized. If I just threw in the Grignard reagent prior to protection, that Grignard reagent probably would attack the aldehyde with more frequency, given that it's more reactive, but it could also react the ketone. It would kind of indiscriminately attack both. So if we want to preserve that aldehyde but react the ketone preferentially, we will react with our 1,2-diol. We're going to assume that that's included in a 1 equivalent amount. And it preferentially protects the aldehyde over the ketone because the aldehyde is the more reactive carbonyl. Once we've protected the aldehyde, we could then react to the ketone with our Grignard reagent and then do an acid workup step. At that point, we still have our aldehyde protected. We could then deprotect by reacting with water and acid. We will hydrolyze the acetal, regenerating the aldehyde that we had originally. So instance number 2 is protecting an aldehyde to then selectively react at a ketone. And we protect the aldehyde preferentially because that's the more reactive carbonyl. Now, instance number 3 is essentially kind of the same situation. We could protect an aldehyde to then selectively react at an ester, or really any lower energy derivative. Looking at the net result of this transformation, what we've done is we've reacted the ester, generating a tertiary alcohol, but we've preserved the aldehyde. Now, to generate that tertiary alcohol, we would have to react the ester with the Grignard reagent. Again, if we were to just throw in the Grignard reagent right away, it could probably attack both, but probably it would attack the aldehyde preferentially, given that it's more reactive than the ester. And so if we want to generate product, Grignard addition product from the ester but preserve the aldehyde, we need to protect the aldehyde first. The aldehyde is more reactive than the ester. We protect the ester, we protect the aldehyde, and then we can do our Grignard addition at the ester, and the ester would react with 2 Grignards. We then work that up, and we'll get our tertiary alcohol. Okay, that's the outcome of reacting our ester with 2 equivalents of Grignard. From there, we can regenerate the aldehyde by reacting with aqueous acid. We deprotect. Okay, so scenario 2 and 3 are more or less kind of equivalent scenarios. We protect the aldehyde to then react at a less reactive carbonyl. Now, this next page kind of summarizes a lot of what we just talked about. Okay, we talked about protecting a aldehyde or ketone prior to forming a Grignard reagent. If I wanted to generate a Grignard from that structure, I have to first protect the aldehyde, reacting with my 1,2-diol and catalytic acid, and then I produce my Grignard. We would then use our Grignard to attack something else. Once we're done with that, we could deprotect. And we already talked about this scenario here, where we could protect the aldehyde to then selectively react at the ketone. The aldehyde is protected preferentially because it's more reactive. We could then do our reaction at the ketone and eventually do the workup and then later deprotect. Now, the fourth situation, okay, let's say the fourth situation for using a protecting group would be to protect prior to forming a phosphonium ylide. Perhaps the objective here is to turn the alkyl bromide into a phosphonium ylide. Remember that phosphonium ylides are reactive towards aldehydes and ketones. So if I just prepared my ylide right away, the idea is I could make the ylide, but then the ylide would react with the aldehydes. Okay, and that would be kind of a comparable scenario to what we showed here. We would generate an ylide reacts with the aldehydes present. And so what I would want to do first is protect the aldehyde, and then I can go through my 2-step process of generating my phosphonium ylide. That would be our fourth scenario of protecting. All right, so we're going to go through now, I think 4 total examples. Looking at this first example, we're reacting the structure here first with Cl2 and FeCl3. That's going to result in an EAS reaction. We chlorinate the benzene ring. And specifically, the OCH3 group is going to control the directing effect. That's a strong electron donating group. Aldehyde is a moderate electron withdrawing group. The OCH3 would control the directing effect. We would direct ortho relative to the OCH3. It looks like ultimately we're going to be preparing a Grignard reagent, but because we have that carbonyl present, before I prepare my Grignard, I need to protect the aldehyde. That's what's happening in step 2. We're reacting with our 1,2-diol and catalytic acid. That's going to generate our cyclic acetal protecting group. Once we have protected the aldehyde, we could then react with magnesium and diethyl ether, and that would then prepare our Grignard reagent. So step 3 is Grignard preparation. We now imagine we have MgCl. Then in step 4, we're going to be reacting with formaldehyde. So the Grignard reagent would then be used nucleophilically to attack the carbonyl carbon. We break the pi bond and work that up, such that after step 4, the acetal is still intact. We have generated a new carbon-carbon sigma bond and generated an alcohol. Okay, the carbon that I'm about to dot in red, that's the carbonyl carbon of formaldehyde. Then from there in step 5, when we react with aqueous acid, we can deprotect. We can hydrolyze that acetal, reforming the aldehyde functional group. So this would be the final structure, wherein the net result is the formation of a new carbon-carbon sigma bond. That would have to be Grignard mediated, and we had to protect prior to Grignard formation because we had that aldehyde in the structure. We wanted to prevent that self-reaction. If we had just put in magnesium and diethyl ether right away, that would have been a mess. The Grignards would have attacked each other. We had to protect prior to Grignard formation. All right. Now, the next three examples I've already drawn all the way out. I'm just going to talk you through them to kind of illustrate protecting group usage and just describe what's happening. In the first example here, it looks like we have an aldehyde functional group and we have an amide. Remember, amides are less reactive than aldehydes. The objective here in this synthesis is to net result reduce the amide functional group. We're going to reduce the amide, but preserve the aldehyde. Now, remember, amides would be capable of reducing, I should say, with LiAlH4. And if I just reacted right away with LiAlH4, that would actually react both the aldehyde and the amide. Both are reactive towards LiAlH4. And so if I want to preserve that aldehyde, but react the amide with LiAlH4, I need to first protect the aldehyde. Step 1, we react with the 1,2-diol and catalytic acid to protect. Now that we have our acetal intact, what we're going to do is reduce the amide. Combination of steps 2 and 3 will result in a reduction of the amide, which forms an amine. Then from there, we're going to react with water and acid, and that step would be deprotecting. We will deprotect the aldehyde, hydrolyzing the acetal. Okay? So here we had to protect the aldehyde because ultimately we want to use LiAlH4 to reduce the amide, but LiAlH4, if I just reacted right away, would reduce both the aldehyde and the amide. So we protected the aldehyde, reduced the amide, and then we deprotected. In the next example, the objective here is to maintain the aldehyde, preserve that net result, but transform the alkyl bromide here and form an alkene bibond. Notice that we've not only formed an alkene bibond, but we've also made a new carbon-carbon bond. This would be a classic scenario of a Wittig reaction. We could take that alkyl bromide, turn it into a phosphonium ylide, and then prepare that connectivity via the Wittig reaction. Now, we have to protect prior to generating a phosphonium ylide from that alkyl bromide. So step 1, we react with the 1,2-diol, catalytic acid, form our acetal protecting group. In step 2, we're going to begin the ylide preparation by reacting with PH3P. Okay, that's going to result in an SN2 substitution. Phosphorus attacks the carbon bonded to the bromine, and we make this phosphonium ion here. Then we're going to complete that ylide preparation by reacting with our strong base and butyllithium will act as a strong base, forming the phosphonium ylide. We deprotonate the carbon and form our phosphonium ylide. Okay, 2 steps to form the ylide. React with PPH3 and an SN2, then deprotonate the carbon bonded to the phosphorus with N-butyllithium. Now that we have the ylide intact, we could react with cyclohexanone. And when we react with cyclohexanone in step 4, we're going to do a Wittig reaction. Those two will react with one another, and we produce this alkene bibond. And then after that Wittig reaction takes place, we could ultimately deprotect by reacting with aqueous acid. Step 5 is deprotection. Deprotection. Now, we had to protect prior to forming that ylide because if I just went right ahead and tried to generate an ylide, the ylide could react with the aldehyde, and that's problematic. We want to protect. Then go through the ylide preparation process, do the Wittig reaction, and then ultimately deprotect. In this next example, we have an ester and a ketone in the same structure. And the objective is to maintain the ketone, preserve that, but react the ester, and specifically react that with the Grignard reagent. Therefore, we need to protect the more reactive ketone to then selectively react the less reactive ester. In step 1, we will protect the ketone. React with the 1,2-diol catalytic acid, we form our acetal protecting group. From there, we can react with 2 equivalents of our Grignard reagent, and that would ultimately cause a decyclization, and there's a 2 times reaction at the carbonyl carbon of the ester, Then in step 4, we deprotect. We could react with aqueous acid, and that will hydrolyze the acetal, regenerating our ketone. All right. So just a few examples of using protecting groups in synthetic sequences. Again, our scenarios for using our protecting groups would be protecting prior to forming a Grignard, and a structure where there's an alkyl halide that we intend to use as a Grignard, and an aldehyde or ketone present, got to protect prior to forming the Grignard. If we wanted to preserve an aldehyde but react with the ketones, preferentially, we protect the aldehyde, then react at the ketone. And if we wanted to protect an aldehyde to then react at a less reactive carbonyl compound, well, we're going to protect the aldehyde, then react at the ester, then deprotect. And then we said scenario 4 was protecting prior to forming a phosphonium ylide. That would be in a situation where we have an alkyl bromide that we want to turn into an ylide, but there's also an aldehyde or ketone present that we don't want to react with.